Good morning, students. Today we will discuss theorems based on bilinear transformations. So the first theorem is to show that the resultant of two bilinear transformations is a bilinear transformation. So let us take two bilinear transformations. The first transformation is W is equal to AZ plus B upon CZ plus D. Here, the determinant of this transformation, which is AD minus BC, that is non-zero. And the second bilinear transformation we have denoted by zeta is equal to A1W plus B1 upon C1W plus T1. Here, the determinant of this transformation, which is A1 D1 minus B1 C1, that is non-zero. So we have taken these two transformations. Now we are to show that the product of these two bilinear transformations is again bilinear transformation. Now let us put the value of W from the equation 1 into the equation 2. When we substitute the value, this equation will become zeta is equal to A1 into the value of W is AZ plus B upon CZ plus T plus B1 in the denominator C1 into W plus T1. Value of W is AZ plus B upon CZ plus T. Now taking LCM and simplifying, we get zeta is equal to AA1 plus B1C into Z plus B1D plus A1B divided by C1A plus CD1 into Z plus DD1 plus BC1. Now here let us denote these four terms by the four symbols. AA1 plus B1C we have denoted by the letter A. B1D plus A1B we have denoted by the letter B. C1A plus D1C we have denoted by the letter C. And D1D plus C1B we have denoted by D. So this equation becomes zeta is equal to AZ plus B upon CZ plus D. Now this transformation will be bilinear if the determinant of this transformation will be non-zero. So let us find the determinant of this transformation, which is given by AD minus BC. Now putting the values of A, B, C and D from here, the value of A is AA1 plus B1C. The value of D is DD1 plus BC1. The value of B is B1D plus A1B. The value of C is AC1 plus CD1. So after simplifying this, AD minus BC becomes A1 D1 minus B1 C1 multiplied with the factor AD minus BC. Now, because the transformation represented by the equation 1, that is bilinear transformation, so AD minus BC is non-zero, and also the transformation represented by the equation 2, that is also bilinear. So A1 D1 minus B1 C1 is also non-zero. So from here we have obtained AD minus BC is non-zero. So we can say that the transformation represented by the equation zeta is equal to AZ plus B upon CZ plus T. That is a bilinear transformation because AD minus BC is non-zero. This transformation is the product of the transformations 1 and 2. So this proves that the product of two bilinear transformations is again bilinear transformation. Now next we show that the cross ratio remains invariant under a bilinear transformation. So let us take four distinct points Z1, Z2, Z3, Z4, and their images we have taken W1, W2, W3 and W4 respectively. Under the bilinear transformation, W is equal to AZ plus B upon CZ plus D, such that the determinant of this transformation, which is AD minus BC, that is non-zero. Now we are to show that the cross ratio of the 4 points W1, W2, W3 and W4, that is same as the cross ratio of Z1, Z2, Z3 and Z4. Now by definition of cross ratio, the cross ratio of the 4 points W1, W2, W3 and W4, that is given by W4 minus W1 into W2 minus W3 upon W2 minus W1 into W4 minus W3. And the cross ratio of these 4 points Z1, Z2, Z3 and Z4, that is given by Z4 minus Z1 into Z2 minus Z3 upon Z2 minus Z1 into Z4 minus Z3. Now let us find these factors one by one. So in general, let us consider the difference of WR with WS. Now WR can be obtained from here by replacing Z by ZR, and that will become A ZR plus B upon C ZR plus T. WS, that can also be obtained from here by replacing W by WS and Z by ZS. So that will become A ZS plus B upon C ZS plus T. Now let us take LCM here. So WR minus WS is given by AD minus BC multiplied with ZR minus ZS. In the denominator we have CZR plus T multiplied with CZS plus T. Now here putting the values of R as one by one, if we put here R is equal to 4 and S is equal to 1, we get the value of W4 minus W1. That will become AD minus BC into Z4 minus Z1 upon CZ4 plus D into CZ1 plus D. Similarly, W2 minus W3 can be obtained from here by putting R is equal to 2 and S is equal to 3. So that will become AD minus BC into Z2 minus Z3 upon CZ2 plus D into CZ3 plus D. After simplifying this expression, we get the product of the factors W4 minus W1 and W2 minus W3, which is given by AD minus BC whole square into Z4 minus Z1 into Z2 minus Z3 divided by CZ1 plus T into CZ2 plus T into CZ3 plus T into CZ4 plus T. Similarly, we can find the value of the product of these two factors W2 minus W1 and W4 minus W3. And that will become AD minus BC whole square into Z2 minus Z1 into Z4 minus Z3 divided by CZ1 plus D into CZ2 plus D into CZ3 plus D into CZ4 plus D. Now dividing these two equations, we get the required equation. So this proves that the cross ratio remains invariant under a bilinear transformation. Now in the next theorem, we will discuss fixed points of bilinear transformation. We proved that in general there are two invariant points for which W is equal to Z, but if A minus T whole square plus 4BC is 0, then there is only one invariant point. And also we show that if there are distinct invariant points P and Q, then the transformation can be put in the normal form. Normal form means the form W minus P upon W minus Q is equal to K into Z minus P upon Z minus Q. And if there is only one invariant point P, in that case the normal form of the transformation will be 1 upon W minus P is equal to 1 upon z minus p plus k. So we'll prove these two parts one by one. So firstly, let us take the bilinear transformation given by w is equal to az plus p upon cz plus t. Now, by definition, the invariant points are given by replacing w by z. So this equation will become z is equal to az plus p upon cz plus t. So from here, by cross multiplication, we get the equation cz square minus a minus t into z minus b is equal to 0. Now solving this equation by using quadratic formula, this will become z is equal to a minus t plus minus under root a minus t whole square plus 4bc upon 2c. So the two values of z we have denoted by p and q. So these are the invariant points for the given transformation. Now, if the determinant of this equation is 0, means a minus t whole square plus 4bc will be 0, then the two roots of this equation, they will be same. So p and q in this case will become same, and their value is given by a minus t upon 2c. Thus we can say that there is only one invariant point if the discriminant of the equation 2 is 0. Now, in the second part, we will find the normal forms. In the two cases, when there are two distinct invariant points, and then we'll find in that case when there is only one invariant point. So first of all, we take two distinct invariant points p and q of the transformation w is equal to az plus p upon cz plus t. Now because these are the invariant points of the transformation, so they will satisfy the equation cz square minus a minus t into z minus b is equal to 0. So this equation will become, when we put z is equal to p and q, we get cp square minus a minus t into p minus b is equal to 0. And for z is equal to q, we get cq square minus a minus t into q minus b is equal to 0. Now from here, we get cp square minus ap, which is given by b minus pt. And from here, we get the value of cq square minus aq, which is given by b minus qt. Now, according to the requirement, let us find the ratio of w minus p with w minus q. Substituting the value of w in the numerator as well as denominator and taking LCM, this can be written in the form a minus cp into z minus p upon a minus cp into z minus q. Now this part is constant, let us denote it by k. So we get the form w minus p upon w minus q is equal to k into z minus p upon z minus q. So this is the required normal form when there are two distinct invariant points. Now let us find the normal form when there is only one invariant point. Suppose that invariant point is p, and we have already obtained that invariant point, that is a minus t upon 2c. Also cp square minus ap, that is b minus pt. Now let us find 1 upon w minus p. Substituting the value of w, which is az plus p upon cz plus t. Now taking LCM here, and after simplification, we get the value of 1 upon w minus p, which is given by cz minus cp plus a minus cp upon a minus cp into z minus p. Now this expression can further be written in this form: c upon a minus cp plus 1 upon z minus p. Now this is constant. So let us denote this term by k. So we get the form 1 upon w minus p is equal to k plus 1 upon z minus p. So this is the normal form. In that case, when we have only one invariant point, which we have denoted by p. So this completes the proof of the theorem.